Hello everyone, I'm Guilherme and I'll be talking about dual time window dynamic MK6040 PET protocols for improved quantification in longitudinal studies and stroke patients. Our motivation here is to perform tau quantification on time activity curves with a break period so that patients can rest during the protocol, and we also want to use reference tissue models to avoid arterial cannulation, and we want that to be a reliable tool for stroke assessment and longitudinal studies of Alzheimer's disease patients. So these methods need to be robust against perfusion changes. To do that, we studied data from 3 healthy controls, 2 patients with mild cognitive impairment and amyloid positivity, and 3 patients with Alzheimer's disease. All subjects underwent a T1 weighted MRI and also an MK6040 PET-CT 90-minute dynamic scans. For simulations, we needed blood input, which was available for all healthy controls for 3 patients, while the last 2 patients we made use of a population-based input curve. Our volumes of interest were inspired by Braak staging, and we also separated Braak stage 3 into early and advanced stages. So from the 90-minute dynamic PET-CT acquisition using the blood data and the reversible two-tissue compartment model, we simulated longer acquisitions of 120 minutes long. From these simulated time activity curves, we could then also simulate perfusion changes by altering K1 and K2 from the two-tissue compartment model. We kept the ratio K1 over K2 constant, and also R1 was kept constant, so that proportional changes in the target regions were the same as the reference region to be used later for reference tissue quantification. So from these 120-minute simulated time activity curves with and without perfusion changes, we could then make the simulation for the dual time window protocol by inserting a break in the middle of it. So this dual time window protocol consists of 3 parts: a phase 1 scan and a break, which together are 90 minutes long, and a phase 2 scan, which starts 90 minutes post-injection and is 30 minutes long. This phase 2 is equivalent to a late time static scanning protocol. We assessed 4 different break lengths, and therefore, as a consequence, also 4 different phase 1 dynamic scanning lengths. And we started with a 70-minute break and made it shorter in each other simulation. So also 60-minute break, 50, and finally 40-minute break. And our goal here was to find the longest break possible while still being quantitatively accurate. This quantification was done with a reference Logan distribution volume ratio. We fixed the equilibrium time at 90 minutes post-injection in an implementation that was independent of the reference tissue clearance rate. We also made a quantification with the standardized uptake value ratios at the average of the last 30 minutes of scan, so from 90 to 120 minutes long. That is equivalent to the dual time window protocol phase 2. And for both models, the reference region was the gray matter cerebellum. And what we found, and you can see here in this plot, is the average DVR bias for healthy control subjects and also the MCIAD subjects for each region. And we saw that longer breaks had an underestimation of DVR when compared to the DVR of the time activity curve without any break. However, with the dual time window protocol with a 60-minute break was quantitatively accurate, as the average bias for healthy controls was less than 1% for all voice, and while for the patients it was less than 5% in all volumes of interest. And that's within the range we can expect for test-retest for this tracer. And now, using this dual time window protocol with a 60-minute break, we can evaluate the perfusion changes. And this is what we see here: the average bias for healthy controls and patients for the reference Logan DVR using the dual time window protocol when there were perfusion changes, and also SUVR from 90 to 120 minutes when there were perfusion changes. And we see that SUVR was more sensitive to perfusion changes than the reference Logan DVR. And if we exclude our simulations where K1 was increased or decreased of 50%, which is a very large change and not really expected in clinical routine, we observed that the reference log and DVR from the dual time window protocol with 60-minute break had an average bias less than 7% for the patients and less than 1% for the healthy controls on average. When perfusion, when K1 was changed up to 25%. While for SUVR, this change almost reached 17% for the patients. So SUVR was much more sensitive to these perfusion changes simulated than a reference log and DVR. And what we can conclude from that is that fluorine MK6240 dual time window protocol with a 60-minute break can be quantitatively accurate with reference tissue models, and it has the potential to improve patient comfort and also use more efficiently hospital facilities. And we also observed that reference log was less susceptible to perfusion changes than SUVR, even when the dual time window protocol was applied, and it would be then recommended for stroke assessment and longitudinal MCI and AD studies. So thank you for your time. Thank you also for my co-authors, and please feel free to contact me via email for any further discussion. Thank you for your time.